Hi class. My apologies for taking a while to get this out. I've kind of been losing my voice from making lecture videos. I was not born to be a YouTube star. So today we're going to talk about homotopy excision and the Freudenthal suspension theorem, and then we'll move on to talk about the Hurewicz isomorphism after this. But I'll do that in a separate video, I think. So one of the reasons that homotopy groups are hard is that they don't satisfy an excision property. Excision would tell you that homotopy groups satisfy homology axioms, because we already have long-exact sequences for pairs, and but excision is not guaranteed for homotopy groups. In fact, most examples that you can look at will clearly demonstrate that you can't have excision. However, you get homotopy excision in a range. So the critical thing is if you have a complex that's decomposed into two subcomplexes. So I've got this A, B, here's C, and all of this is X, right? Then, and we're requiring our intersection to be non-empty, then if the pair A, C is M-connected, so its homotopy groups of the pair vanish below M, and B, C is N-connected, and both of these are going to be required to be positive or non-negative integers, then the induced map from the pair A, C to X, B is an isomorphism in a range. So provided pi I is below M plus N, you actually get that this is an isomorphism, which is what you would expect from excision, right? So this is like I'm trying to remove the subgroup or the subspace C, and so A relative C and X relative B, which is like the bigger extension of C, right, should give the same homology, relative homology groups and cohomology groups. But on homotopy theory, that's not guaranteed, except if you're in this range. So in low degrees, you can guarantee this provided you have some bounds on connectivity, which are given here. And also in the next degree up, it turns out to be a surjection. This is just, the sort of thing you would expect in long-exact sequences. So I should note this inclusion, this map on homotopy groups is induced by the inclusion from the pair A, C to X, B, as you'd expect. So we're going to prove homotopy excision, but I want to talk first and prove one of the most important consequences of homotopy excision. So one of the things that homotopy excision does is it tells you that there is actually a range where homotopy groups look like a homology or cohomology theory. It turns out that homotopy groups look most like a homology theory, and cohomotopy groups, which are maps into the sphere, end up looking like a cohomology theory. But that doesn't really matter. But it's only in this stable range, as it's so called. So Freudenthal suspension theorem gives us this the so-called stable range where homotopy groups behave more like a homology theory, in particular homotopy groups of spheres. So let's look at the statement of this and then prove it. So the version 2 is the more general version of the Freudenthal suspension theorem, but version 1 is, I would say, how most people remember it in their brain, which is that the suspension map from Sn to Sn plus 1, so this is, I need to give a map, let me get pens all sorted out. Okay, so I need to give a map from pi I of Sn, and what that is the homotopy classes, remember square brackets means homotopy classes, of maps from Si to Sn, but both of these, there's a map from homotopy classes maps from Si to Sn to the homotopy classes of maps from Si smash S1 to Sn smash Sn, or sorry, S1, right? And so this is the suspension of Si, and this is the suspension of Sn. But suspension on spheres is precisely raising the dimension of the sphere by 1. So this looks like Si plus 1 to Sn plus 1, which is in turn definitionally pi I plus 1 of Sn plus 1. And so this is the suspension map, or suspension homomorphism. In case suspension is not something you've thought about in a while, the way to think about suspension is that suspension of some space X looks like it looks like you've glued two cones together along X. There's one way to think about this. So your picture might be that if this is your space X, let's draw a different color. I've taken a cone on X up top, and also a negative cone on X down below, and additionally, in order to get the reduced version, you want to mod out by whatever the base point of x0 is in both of these. So you're basically reducing your choice of base points. So you have the kind of this additional map. So people also like to write this as, let's see, as x cross S1 mod x wedge S1. Those are equivalent. Or as x cross I, and then modding out by the union of the spaces x cross 0, x cross 1, and x0 cross I. And so in that picture, you would have something like this cylinder. And so here's my copy of X that lives in the center. And what I'm modding out by is this top, this bottom, and this point. And the green thing becomes my base point. So this looks like X with two cones on top of it. And the base point is over here. So all of this, it just goes to show you, I don't know, it's just reminding you what suspension is. So the suspension map is an isomorphism, is what Freudenthal suspension says, when I is less than 2n minus 1, so in low degrees. Let's write like this. Roughly less than twice the dimension of the sphere, and is a surjection in that next degree up. And if And more generally, if X is a CW complex, which is n-1 connected, so in particular, this is true for Sn. Sn has no homotopy groups in degree n-1 and below, so it's n-1 connected. You get that the suspension homomorphism for X, which is defined the same way, just I need to replace this with, well, nothing, that stays outside, but this becomes X. And so it's just a match to the suspension of X is an isomorphism in the same range, I less than 2n-1, and a surjection degree 2n-1. So let's prove Freudenthal suspension assuming excision. So what we should do is deconstruct our space, suspension of X, it's right in black, suspension of X. I'm going to break that up into the cone, let's say the positive cone on X, and the negative cone on X, and I'm going to just consider these as subspaces. So I've got here's X, here's cone plus on top, and cone minus on the bottom. So here's A and B, etc. And so the intersection of cone plus and cone minus is the space X, concentrated right here at the equator. So the blue X is the one we care about. And we just double check the relative groups. So if you take the, so to check excision, we need to look at the homotopy groups, or the connectivity of the pairs. A cone on X, either cone, comma X. And so to get this, we're going to look at the long exact sequence for the pair. And this is just for the cone, right? So pi I of X, absent pi I of plus or minus cone, either cone on X, maps into pi I of the cone on X, relative X, pi I minus 1 of X, etc. And what we notice is that the cone on X is contractible, so this is always trivial. And so we actually get an isomorphism between these pairs of groups, because the next group is also 0, always. So pi I of Cx comma X is pi I minus 1 of X. And by assumption, or by the hypothesis, X is n minus 1 connected. So pi I minus 1 is going to be trivial whenever I minus 1 is less than or equal to n minus 1, which means that I is less than or equal to n, which means that, in fact, the pair is n connected. So both pairs. This now means that the suspension map, which is induced by the inclusion of C plus X relative X, so let's include this way. So I'm taking one of these into the whole space, so that's the whole suspension of X relative C minus of X. So just to be clear, here's my like A relative C group, and here's my total space A union B relative B. Maybe I should write C as A intersect B. right? And so this is my inclusion map. And by excision, I get to conclude that this map is an isomorphism for, so I look at on pi I of this map, whatever, for I less than 2n minus 1, and is a sorry, it's Freudenthal conclusion. I less than n plus n, because each pair is n connected, and a surjection for I equals n plus n. And now we check and see that the cone of x relative x, that looks like a copy of the suspension of x. So, because these are all good pairs, so I can like mod out. So this looks like pi I of the suspension of x. You know what, that's maybe just needlessly complicating it. We know that pi I of the cone of x is the same as pi I minus 1 of x. So this is pi I minus 1 of x. And on this side, this is isomorphic to pi I of the suspension of x, because you're taking the cone on x and you're collapsing, sorry, you're taking the suspension, but you're collapsing everything below here, right? If this is all collapsing to a point, what you get is just like a new, you pick your equator to be halfway up here, and now this is what it looks like, which is still a copy of the suspension. It's just half as big, but that's, you know, that's not a topological thing, that's just the same. So yeah, so that looks good. So what's our conclusion? It better be the correct one. So I guess I had a shift of I minus 1. So I ended up looking at the map from pi I minus 1x to pi I the suspension of x. And this is an isomorphism for I less than 2n, and a surjection for I equal 2n. And so if I plus 1 to all of these coordinates, I get I plus 1 to I, which will become a minus 1 on the other side. Yeah, so yeah, this is what our groups end up looking like, which is exactly what we claimed. And now, since the sphere Sn is n minus 1 connected, we can use this proof to prove Freudenthal suspension for spheres. So let's look at the Freudenthal suspension theorem in the homotopy groups of spheres. So this is a chart of the stable homotopy groups, or sorry, the unstable homotopy groups of spheres. So these are the unstable homotopy groups. And you'll know I'm graphing pi I of Sn, and pi I, the groups go to the right, the sphere dimension goes down. So what I've done is, in gray, very lightly, I've drawn all the 0 groups, and so the ones that are over here we know are 0 just because of connectivity of the spheres, so there's no maps from low spheres to high spheres, right? And we've seen that. These all being 0 is just because pi, the universal covering space of S1 is contractible. So, and pi 1, yeah, we've seen this. The higher homotopy groups of S1 are 0. But then these other groups, I've color-coded them. So the blue range is the stable range. And the red guys are the surjection from pi I Sn to something that will then be in the stable range, pi I plus 1, Sn plus 1. So these boundary things where I is exactly equal to 2n minus 1. So you can see as we go down that Z starts existing here and then is the same as we go down along this diagonal. Z mod 2 starts existing here and goes down stably. Here's the third stable homotopy group of spheres, which starts existing here. And so they're indexed by how many, so the 0th stable homotopy group of spheres is the one that is I plus 0. So the standard notation for this, I'm going to scroll down slightly, don't want to go too far off, is the pi I stable of the spheres, which is sometimes the sphere's spectrum part is just omitted, is defined to be pi I plus I plus n of Sn. And so we enter, so pi I looks like when I is 0, it's Z, and then we can see it becomes Z mod 2, and then it's Z mod 2. The next one we see is this Z mod 24 that starts existing here. And then we see this 0 and this second 0. So the range, the stable range that we can see is Z mod 24, 0, 0. So that's I 1, 2, 3, 4, 5. And then I'll just put dots here because it's definitely not 0, but forever. But that's a cute place to stop. And these are the first stable homotopy groups of spheres. But it's worth noticing what's happening at this kind of like semi-stable boundary. So that Z is surjecting onto the Z mod 2. This Z mod 2, it turns out, is actually an isomorphism with the next Z mod 2. So in some sense, this class exists 1 degree earlier than it's guaranteed to stably exist. This surjects, and there's a couple ways you can write a map like that, so we don't know what it is exactly. But then you notice, like, sometimes this is surjecting onto 0, so that's just a class that dies. And the same with this copy of Z here. It dies and goes to 0. In fact, secretly, there's a theorem in play that none of these stable homotopy groups past this first one can be infinite. So they all have to be finite cyclic groups or just finite abelian groups, right? So products of them and stuff. And so you can actually, from that, if you know that theorem, you can conclude that this Z here has to die because it doesn't persist. But it could have turned into a Z mod 2 or a Z mod 4 or something like that. And so it's worth wondering about. The other thing I'm gonna point out is that because of the Hopf fibration, we have this, and the fact that pi I of S1 are 0 in high degrees, we actually have this like isomorphism, how do I want to write this, between these groups vertically. And so there's also this pattern here in these low degree stable groups where pi, the higher homotopy groups of S3 and S2 look very similar with no degree shifts, except in this very lowest range where there's in S2 there's a ZZ, and in there's a ZZ Z mod 2, and in S3 it's a 0Z Z mod 2, and so this is maybe an interesting little area to look at. But above this blue part of, blue shaded part of this diagram, you get a lot of complicated looking garbage. And so, right here, like all this stuff over here is hard and unstable. So you don't really have control over it, and it can look very complicated and messy. And you can see we've got all sorts of complicated groups there. But the stable range is kind of nice because we are guaranteed the existence, the stability of these groups along these diagonal lines, which are the suspension homomorphism lines. So one corollary that we get out of the Freudenthal suspension theorem and our understanding of the spheres is that pi n Sn, this copy of Z that we have on this diagonal above, is in fact an isomorphism and is generated by the identity map. And I realize right now that I actually did make a little mistake up here, so I'm going to correct it. The mistake is this group right here is actually also in the semi-stable range. And so we have, that should be red with the surjection coming out of it. And that matters fundamentally for this proof because basically we know that's a surjection, but because it's a map from Z to Z, which we've already identified, both groups as Z, and it's a surjection, we know that it's an isomorphism. So we actually know that all of the first stable homotopy groups of the sphere, all these copies of Z here, are isomorphic with pi 1 S1, which we know is generated by the identity and admits an isomorphism via the degree map. So let's just write that out down here. A proof for this might look like that we know pi 1 S1 surjects onto pi 2 S2, which is then lives in the stable range. So this is isomorphic via suspension to pi n Sn for all n bigger than or equal to 2. But we also know that this is Z, and we know this is isomorphic to Z via the degree map. So by evaluating degrees of maps of S1, self-maps of S1, we know that pi 1 S1 is isomorphic to Z, and we also know that this group is isomorphic to Z, and so this has to be an isomorphism. The surjection is an isomorphism. Let's maybe write that for legibility in a different color, because this is a thing we concluded. And now I have a ton of isomorphisms, so I just know that all of these things are isomorphic via the degree map to Z. This also tells you how to generate elements of arbitrary degree in pi n Sn. So, for instance, the element D in pi n Sn can be represented by a self wrapping the equator of Sn. So if I draw, here's Sn, and then I look specifically at the equator, Sn minus 1, I can wrap that to itself by a self-map. That's multiplication by d. That's the d-fold suspension map. And this gives a map, I've drawn it by this little squiggle here, from one sphere to the other sphere. So the image of it is something like, if this is going like, kind of like that for RR2, then you can imagine extending this up to give like a little twisty cylinder. And then at some point you have to cone off this cylinder to turn it into an Sn. And this, by shrinking down these pinchy things to the north and south pole, you'll end up with a continuous map of Sn to Sn by taking one inductively from Sn minus 1. And in particular, you can start with S1 to S1, which is really just the default wraparound map that we talked about last semester when we talked about covering spaces. Let's put a little QED box down here because we finished this proof. So how do we prove excision? Honestly, it's terrible. The proof is like really, really bad, and I don't think anyone remembers it because ultimately it amounts to really careful homotopies so that you can come up with like simplicial arguments around these maps. And so, like, ultimately, even in the case where C is just being, where like A is E is like adding an N cell to C, and B is like, maybe this is a different dimension, but it's adding an M cell to C. And now I have to think about connectivity. I think I mean to say +1 cells to have the correct connectivity. Even in this case, you ask yourself, okay, if I have a map from Si into this, it's doing some sort of, messy stuff that goes over both of these regions. And you're going to have to homotope it so that you can split it so that in like the pre-image of every cell, this is compact, so you know that it only intersects every cell finitely many times, and so you have to homotope it to get a new map Si into X with the property that like F inverse of each of these cells is like a finite disjoint coproduct of like sigma k's, where k I guess depends on alpha for some alpha, right? So like each of these you can break this up so that you are just going into A and into B a certain number of times. The rest of the time you're staying in C. And the same for F inverse of En plus 1. And then you have to start carefully edging your homotopy over so that you can relate these relative pairs. And it's just bad. So if you want to see details, you can try reading Hatcher. It's legitimately one of the most illegible proofs in the book, but I'm gonna just take homotopy excision as a given and move on with getting kind of like the more important consequences. So you should view homotopy excision as a technical tool to get Hurewicz and to get Freudenthal suspension theorem. So let's say big picture is that excision, so homotopy excision is a technical tool to give us Freudenthal and other results. And it's those other results that are the like moral takeaways of what homotopy excision is doing that we're going to focus on. So let's compute some homotopy groups. The first space we'll look at is a wedge of copies of Sn, and we can do this either in two cases. So either alpha is finite, or alpha is infinite, and we can sort out what goes on in both of these cases. I'm restricting to n greater than or equal to 2 because we already know that the infinite wedge or the finite wedge of S1s, we know how to do the pi one using Van Kampen's theorem. And so that part we know is kind of easy, but then, although the infinite wedge is nasty, but we've addressed this before in the earlier chapters, and pi I with I strictly bigger than or greater than or equal to 2 is all 0 for the wedge of S1s, because of course pi I of S1 is 0 for all I bigger than or equal to 2. So let's first focus on the interesting case when n is bigger than or equal to 2. And so one of the things we can do is we can look at the coproduct, the wedge sum, living inside of the product of SNs, right? So, like if the Cartesian product looks like this, then you always have inside of it the coproduct living inside. So we're at base points, right? So one of the things we notice is that this guy here, since n is bigger than or equal to 2, pi, or the big product, SNs, only has cells in dimensions k times n. So, and that this goes up to alpha n, or I should really say alpha is in a set A, So this goes up to magnitude of A, n. Right, and this is just coming from the CW product cell structure. Now, the wedge, this guy has cells in, or its cell structure looks like it's got a base point, E0, and then it's got magnitude of A distinct n cells, right? Because it looks something like this, right? And that means that the wedge product is the K-skeleton. I don't remember what our notation for this was, but the N skeleton for the product. Because all the higher cells live in higher degrees, like all the new cells in the product. Now, the degree we actually cared about was n, though, right? So this implies that on pi n, the wedge is isomorphic to pi n of the product, and homotopy groups and products commute with each other. So this looks like a big direct sum over alpha of pi n s n. And so that this is our answer for what it looks like. And in the infinite case, it will be the same. But this direct sum is now infinite. And the way we prove it is we just take a map from the direct sum to pi n of the wedge. And where does this map come from? It comes from just including Sn into the wedge. And you do this for each alpha. So inclusion alpha into there. And then you're adding these all up. And so every time you have a map into one of these Sn's on the left, it's just telling you what index to land in your wedge sum on the right. But then you notice that Sn is compact. So each element, let's say alpha I've already used, A, over here, lands in finitely many summands. And this then implies, oh, you know what, let's just, if A is over on the right, it lands in finitely many summands, which means that you can pull it back to having 0 in all the other summands, and therefore the map is surjective. So A is in the image of this map. And injectivity, well, if two maps, or if a sum where all but finally many are 0 on the left maps to 0, then there has to be a null homotopy, but that null homotopy on the right lands in finitely many things, so you can pull it back to be a null homotopy on the left. So, put another way, if we have B here, if B maps to 0, then the class that B, that null homotopy documenting, I should really give a name to this map, let's just call it phi B, is null homotopy via some homotopy H to 0 in the target, and then both phi B and H land in finitely many cells, many summands. So you get to pull them back as well, and this proves injectivity. So in both of these cases, you get this formula. Let's look at one more example. Another example is, let's take Sn wedge S1. So this space, right, looks like S1. Here's my copy of Sn, right? And my base point is that guy right there. We know that we can pass to the universal cover. Let's call that E, and pi n of E, let's just say pi I of E is isomorphic to pi I of Sn wedge S1 for all I bigger than or equal to 2. We proved that when we first got into talking about higher homotopy groups. Not hard. Then what does the universal cover look like? Turns out it's pretty easy. You just take R, and then at every integer, you wedge with an Sn. All right, so it's an infinite string of balloons. Now this is clearly homotopic via a deformation retract. So if I contract the copy of R to 0, so I end up gluing all of my integers together. When I do that, I end up with this infinite bouquet of spheres that we studied before, alpha in, I guess, Z here, of Sn alpha. So we get to conclude also that pi n of Sn wedge S1, if n is bigger than or equal to 2, this is isomorphic to this big direct sum of pi n Sn's alpha in Z, which now looks like just a big direct sum of copies of Z, indexed by the integers. And so this just goes to show you that it's our like slogan-y takeaway from this. Put a QED box on that. Pi n of a finite CW complex can be, let's say, quite infinite. Right, so this was almost the easiest CW complex we could have come up with, right? It has 3 cells, E0, E1, and En, right? And lo and behold, it has infinitely many, or infinite pi n even. So just by adding that one extra En, we just totally fucked ourselves up. So I would point out, you can see the action of pi 1 on pi n here, right? So if you have some degree D map, for instance, that's maybe D in this coordinate, so D in maybe D0 in this coordinate, maybe it's just the identity here, so it's D1 equals, so maybe here D0 is 2, D1 is 0, maybe this one's also D2 is 0, etc., right? Like, this would give you, this sequence would give you an element in pi n, and you can see that if you act by the generator living in pi 1, it shifts to the right. And so I should have drawn this sequence as having integer many elements, so it right shifts. So adding +1 is right shifting. So let's just say over here d minus 1 is also 0. It would give you 0, 0, 2, 0, 0, right? And if, I guess I've also written the d minus 2. I don't know, I should have just gotten rid of that. Yeah, that looks good. Let's just erase some of this. Yeah, so takeaway is that homotopy groups are really hard, the higher homotopy groups especially, but in the universal cover picture, you can actually see the action of pi 1 very easily in these sorts of examples. So let's finish out by giving another interpretation of excision in the case of pairs, CW pairs. So the idea here is that one of the things we knew about CW pairs is they were nice pairs, so their quotients, so like relative homology looked like homology of the quotient for them, or the relative homology looked like the reduced homology of the quotient. So the same thing is sort of going to be true for homotopy groups, but only in the stable range. And so if we assume the pair is R-connected and A is S-connected, the range ends up being that for I less than or equal to R plus S, we get an isomorphism, and we get a surjection at R plus S plus 1 between these pairs. And let's prove this. So the way to prove this is to definitely take a cone on A. So your picture should be like, I've got A, I got X, and the best model for X mod A is putting a cone on A, and then that looks like X mod A. And so in particular, what is this space? This is X union over A with a cone on A. Yeah. So we have definitely proved this previously. I think when we proved, like last semester, when we proved that, in fact, good pairs, or CW pairs are good pairs, that they model like quotients like this, we proved that, in fact, this union is homotopy equivalent to the cone like this. So, yeah, so, I don't know, maybe you should see this as being like X union A of the cone on A mod the cone on A. So even if A is not a CW space, but X is relatively CW to A, this ends up being a good model for the quotient, i.e. the cone on A is a closed inclusion inside of X in this case. Anyway, so what does this tell us? Well, we should look at the map from pi I of X relative A, and I'm cutting away A, so this should look the same. So I'm decomposing X union the cone on A into the cone on A union, so here's like my A part. Too many A's, I'm so sorry. Union the X. So that is to say, I'm decomposing this space and I'm doing excision. So the intersection here is A. This is definitely writing the same thing over here as over here. I'm so sorry. But maybe this would be my, yeah, I don't know. So I'm taking this to be B in the excision theorem, right? That's what I'm trying to say. And X to be A in the excision theorem. There we go. That's fine. I'm going slowly insane. So by excision, X rel A should be the same as pi I of X union A conon A relative conon A. And this will be an iso for what was our assumption about X rel A's? Right, so by assumption, what was it? We have XA is R connected. Yep. So we have X rel A is R connected. And the other pair that we have is the conon A relative A, because A is the intersection. And A is S connected, which means that the conon A rel A, which looks like the suspension, is S plus 1 connected. So this is an isomorphism for I less than R plus S plus 1 minus 1, and a surjection at R plus S. Oh wait, I'm using the Freudenthal notation, but that's not for excision. You just add the connectivities. So this is R plus S plus 1, which, and then it's a surjection on the equality. And then, let's see, what do I want to do? X union A, conon A, relative conon A. Conon A. This is contractible. So something relative, it's a contractible subspace that's exactly the same, it's isomorphic to the homotopy groups of X union A conon A. And we said, that's homotopy equivalent to X mod A. So this is pi I X mod A. And this now gives the exact result we wanted. Let's just double check. Isomorphism on I less than or equal to R plus S, and surjection on R plus S plus 1. Yep, that's exactly what we have. So we've done it, finally. And this total composite is induced by the quotient map, where we've contracted the conon A to a point. So that looks good. How much more space do we have? A little bit more. Okay, so maybe the last example we'll consider in our quest to get any group we want as a homotopy group is we'll let X be, let's take this giant wedge of SNs that we have, and then let's add a single cell. Let's add a single cell En plus 1. And the attaching map here is phi. So, yeah, maybe, yeah, let's add that many. Let's add a whole bunch of new N plus 1 cells and compute what pi n should be. And our expectation is it should definitely be a free abelian group mod some relations. So these should give me free generators, and these should give relations. on pi n. And so let's just double check that in fact that works. So let's write alpha or phi beta for the map from boundary en beta. I guess I'm writing this as like a big, I've taken a whole bunch of these. So, mapping to Sn into the big wedge, right? This runs into finitely many cells, so, right, and what is this boundary? This is an Sn minus 1, plus 1, Sn. So this lives in pi n of the wedge, which is the direct sum over alpha of z's, right? So we've picked our relations to be just, some elements that we've chosen to attach cells to inside of there. And so the claim will be that pi n of x, let's put it this way, pi I of x looks like nothing in degrees I less than n. It looks like a free abelian group on a bunch of generators mod the relations alpha b when I equals n, and it's totally unknown what this is when I is bigger than n. And so the only part of this, so let's indicate the proofs because I'm running out of space, but I want to be done. So this part, this is just cellular approximation. Put another way, we already know that adding n plus 1 cells can't change the homotopy groups in degree n minus 1 and below, where it already looks like this wedge of spheres and has zeros everywhere. So, like, the fact that we checked that pi I less than n of Sn is 0 now carries over. And then in this 1 degree, the thing we want to look at is the long exact sequence. So we look at pi n plus 1 of x relative its wedge to pi n of the wedge to pi n of x to, well, it has to be 0 for degrees below this. It would be pi n of the pair, but the n skeleton of x is concentrated in that degree. So, this, by our preceding corollary, this looks like pi n plus 1 of a bigger wedge of n plus 1 spheres. Because if I take, and that's not over alpha, but over beta. Right, so if I take all of these, if I contract away this point, if I collapse this, what I get out is just going to be a wedge indexed by beta of the En plus 1s. And these are n plus 1 cells, so they look like Sn plus 1s in this setting. And now our previous work implies that since the boundary map here is going to send an element in here which is generated by E beta, to phi beta in here, we have the correct presentation for pi n of x from this little short exact sequence of groups. So yeah, that looks good to me. So this is telling us this claim as desired. So in the next lecture, we'll talk about Eilenberg-MacLane spaces a bit, and probably the Hurevich homomorphism. But we've been doing some of these like designer homotopy group spaces for a while now, and you should think of X as just another one, where if I now want to build a space which has no homotopy groups in any degree up to degree n, then it has a designer abelian group in that degree n that I've specified by generators and relations, then the space I produce now has kind of like weird homotopy groups in high degrees, but from our techniques in cellular approximation, we know that we can kill these by attaching higher degree cells, and therefore produce Eilenberg-MacLane spaces who have the given homotopy group in degree n, and nothing in any other degree.